We've studied gases earlier in the course, and we use the ideal gas approximation that each gas molecule is doing its own thing, moving freely about and filling the container it occupies. Unlike gases, liquids and solids are condensed phases that arise because intermolecular interactions exist between individual molecules. Given a sufficiently low temperature, a gas condenses into a liquid where the molecules are allowed to come together and interact. However, the molecules are still relatively free to move around, and a liquid thus adopts the shape of its container. Finally, given an even lower temperature, molecules become fixed into positions that optimize the intermolecular attractions between themselves, thus forming a solid that keeps a rigid structure. Though many different intermolecular forces exist, the most important is the hydrogen bond. In a hydrogen bond, a hydrogen bound to either a highly electronegative FON or Cl atom has a substantial partial positive charge. Obviously, the FON or Cl atom correspondingly takes on a substantial partial negative charge. This positively charged hydrogen atom of one molecule then interacts with the negatively charged atom of another molecule. This intermolecular force can be as high as 10% of a covalent bond, so hydrogen bonds are by no means negligible. Hydrogen bonding is particularly important in water, where each molecule can participate in 4 hydrogen bonds, twice as an H atom donor and twice as an H atom acceptor. Hydrogen bonding in water accounts for its unusually high boiling point for such a small molecule, its high heat capacity, and the unusual property that the liquid is actually denser than the solid. Phase transitions, such as boiling, are regulated by the intermolecular forces. In general, the stronger they are, the higher the boiling point has to be to drive the molecules apart into the gas phase. Equilibria also exist between phases. Using water as an example, at a pressure of 1 atmosphere, the solid and liquid phases are in equilibrium at 0 degrees Celsius. Meanwhile, the gas and liquid phases can be in equilibrium at any temperature, with the pressure of the water vapor being called its vapor pressure. However, at 100 degrees Celsius, liquid water and water vapor at a pressure of 1 atmosphere are in equilibrium. For any liquid at its normal boiling point, its vapor pressure equals 1 atmosphere. The equilibria between the phases is summarized in a phase diagram. Its x-axis is temperature, and its y-axis is pressure. The diagram is split into 3 phases. To know what goes where, just remember that at any given pressure that goes through all 3 regions, low temperature corresponds to the solid phase. And as temperature is increased, we go through the liquid region and finally into the gas region. We also keep in mind that water is unique in its phase diagram in that increasing temperature means going from solid to liquid. In a phase diagram, this is seen by the negative slope of the line dividing the solid and liquid phases. All other substances tend to have a positive slope for this line, meaning that one goes from liquid to solid as one increases the pressure.